we have Nika, who will be talking about incentives and personal learning theory guarantees in federated learning. Nika is an assistant professor at UC Berkeley. She broadly works in theoretical aspects of machine learning and algorithmic economics, with the focus on contributing to the foundational perspectives on interacting learning systems and social and strategic agency. She's won numerous awards, but very excited to hear her talk.
Thank you. Thank you so much for the invitation. I'm really excited to be here to talk about collaborative learning. And I feel like the past two talks were a really great introduction to the type of things I'm going to be talking today. So I'm going to talk about, broadly speaking, training and also training while having in mind incentives of agents in collaborative learning. This is a joint work with a number of people. This is actually based on a number of joint work with a number of people. Some of them are with Mike, who is here, but there are also colleagues like Arvind Blum and Ariel Pukacha who are not here. There are also 4 PhD students who've contributed to this line of work, and they've done a great job. Richard Phillips from Cornell, Ming-Da Chow from Stanford, Eric Zhao from Berkeley, and Han Zhao from TTIC. So what I want to talk about today is that we've all heard and experienced this emergence of big data and the fact that we have a lot more data to be dealing with today. In fact, the applications that we're also using and many of the modern applications of machine learning also requires a lot of data. But what's happened in recent years is that not only we have more data, but this data is also coming from many different people and many different stakeholders. So with more data, now we are also dealing with more stakeholders. And this brings these additional considerations that traditional ways of looking at machine learning didn't necessarily have to account for. So we need to think about these stakeholders with their individualized objectives, with their needs and limitations and aspirations and dreams that they might be having. So what are some of these examples? The first one is ownership of data. For example, data is often separated to many different, is owned by many different agents. And in fact, we do need them to collaborate and share this data together. A great example of this is like large genome studies that require such a large scale amount of data that no one institute actually owns that much data. And recent advances have really come about with kind of hundreds of institutes working together and actually sharing their data. There's also the idea of per group guarantees, where not only data is actually owned by different agencies, but different agencies actually represent different sections of populations, and they care about well-being and accuracy of the classifier on those populations. So this is another example where medical research is also very relevant when we're thinking about kind of providing solutions that make sense for the different localities, different populations, or different models and different scenarios that are represented by different agencies. And lastly, there's the issue that beyond accuracy and beyond ownership of data, there are all these external objectives, like wanting to, provide as little either statistical or computational resources while getting the most out of this collaboration, or perhaps competition or other aspects to what these collaborations might look like, that we need to now think about in our design of algorithms, but also in the theory of sample complexity that we're designing for these areas. So this is kind of broadly speaking what I'm going to be talking about, that we have more data, more stakeholders, more and newer challenges. And the 2 challenges that I'm going to be talking about are these dealing with individualized and heterogeneous learning objectives across different groups, and also these external objectives as a whole, and mainly the idea of how to deal with costly samples and what's the theory of sample complexity that will address these things. And at a high level, what I really want us to have in mind is that we know collaborative learning holds immense potential, and it holds that immense potential if we can actually have large-scale kind of collaboration. So that large-scale impact requires large-scale collaboration and mass participation, which means that we do need to recruit and retain people in this. And this whole line of work is about how do you provide guarantees that would help us recruit and retain agencies. So I want to start with why we should be thinking about per group learning guarantees, and I'm sure that many of you have already thought about that, and also we saw some examples of this. But the reason I want to still go over it is that the typical way of approaching federated learning algorithms is supposed to work well on average over data sources. So this is good for learning across sort of different data centers, or where the data is separated to agents kind of randomly and these data sources are kind of homogeneous. But what's happening is that nowadays we are applying the same algorithms not to just data centers, but to actually data that is human or organizational data that is very heterogeneously separated across different sources, different agents, and different data sets. And for these non-homogeneous tasks, I mean, you can sort of mathematically, in theory, realize that it's not that hard to say that my model has 5% average error, but actually it has 50% average error on 1/10 of the agents. So this is pretty bad for that 1/10 of the agents. And it's actually not that far from something you can observe in actual data sets. So it's not just some mathematical equation, but it's something that you also see in some data sets where some data sets and tasks are much harder. So if you are only thinking about providing average accuracy, you would kind of require very little amount of work, maybe very few iterations of optimization or very little like small amounts of data. But then if you are thinking about making sure that the accuracy of the task for every agent is high, then you have to do twice as much number of iterations and actually maybe 50 to 100 times as much as data. So now that we know that this is a real issue that happens in very simple, in fact, data sets as well, what you really want to do is to think about how to account for this type of task difficulty. And the fact that some populations are easier to learn than others. And this also depends on kind of not a single population at a time. It also depends on the relationship between multiple populations. So if we are going to have a theory about sample complexity, it has to be something that addresses the fact that these tasks are difficult in different ways. And it doesn't really say that I need to have like a fixed number of samples per agents, but rather think about how to approach taking samples when the need arises. So really what we're trying to do is that how can we ensure that every learning agent has high accuracy, but still use reasonably small amounts of data. So this is what I've been calling, This is what I've been calling collaborative learning model. And the way to think about it is that you have K populations. These are shown by distributions D1 to Dk. And at a high level, what you're trying to learn is a model whose expected loss is small for every single one of these distributions. So the max loss is actually small. This is possible if these distributions are kind of close enough to each other. Maybe they share actually the target classifier, but maybe their marginal distributions are different. So this is kind of providing universally good model. But you can actually generalize this to any set of distributions without making any assumptions by saying that I want my max loss to be as small as possible. So this min max is the smallest you could have guaranteed. And maybe there is a little bit of an epsilon that's okay if I don't quite match the truly optimal thing to do. So this is a more general setting. Both of them, we can, from now on, let's call them collaborative learning for this talk. And then the question is how much data is, sufficient and necessary to actually provide this type of guarantee. So note that if I didn't have these maxes, this would have been the traditional either agnostic or pack learning models from cycle. And with this max, you're essentially trying to extend those guarantees from single population to multiple populations. This is a unifying perspective. And while I've been calling it collaborative learning, actually within a span of 2 to 3 years, several different communities started talking about essentially this problem, but using different language. And sometimes with ideas or concepts coming from fairness, robustness, collaboration, and federated learning. So I wanted to highlight 3 of these, and I'm sure you're at least familiar with 1, maybe 2, maybe all 3. So the first one is this the collaborative learning work that I introduced in 2017. Soon after, around the same time, in fact, 2 other works were agnostic or fair federated learning by Mohri and others, where it's the same model essentially, except these DIs are representing sort of client distributions with having fairness as a goal in mind, that this max-min is kind of a, min-max is kind of a fairness objective. There's also group distribution and robust optimization, where DIs may represent sort of distributional shifts or other ways of thinking about robustness or, again, fairness goals. These are just 3 examples. More recently, if I go back, I keep seeing this kind of model being referred to by many different names in the past 2 years. So I think it's actually nice to think about them in a unifying perspective to see how we can address all of them at once. So we are going to look at some mathematical theory for how many samples or how much information you need to address these problems. And I'm going to start with a trivial statement almost, which collaboration needs interactions. Well, this is probably not surprising, but let's see truly if it's not as surprising as we have thought in the past. So what's the trouble with the standard algorithms and settings? And these includes the typical way of looking at agnostic federated learning or group DRO, is actually lack of interactions. And I mean this, that except to perform some distributed computation, there's not much interaction happening between different parties. Like the number of samples I provide, the number of my learning rate, how frequently I update something. These are all decided in a non-interactive way, and usually at the beginning, or even if it's not necessarily at the beginning, it's still not something that takes into account the performance of the model on other agents. So this is what it means to be non-interactive, even though you're sort of distributedly computing these things. And if you think about this kind of a non-interaction, what it's really ignoring is what we wanted to not ignore, which is the fact that the tasks have different levels of difficulty. And this different level of difficulty is not just defined by your own task, it's defined by your task with respect to everybody else's task. So to not have this type of interaction is essentially missing on the important help that collaboration can provide. So what we formally showed in this paper was that if you don't have interaction in this language, we said you're still allowed to do distributed computation, but non-interactively, then the sample complexity of solving these k tasks is k times the sample complexity of solving one of them. What this is saying is that essentially collaboration without an interactive protocol is almost as ineffective as not collaborating at all. Because I could have thought about a world where instead of collaboratively solving this, I would just try to learn every distribution independently. So interaction is really important to actually do better than not collaborating. And what I will talk about a little bit is the fact that if you now do allow interactions, you will see a huge benefit, which is that instead of having a linear dependence on the number of agents, you're now going to have a logarithmic dependence on the number of agents, or better. So this is to formalize what I meant a little bit more with actual math. And I wanted to say that, so this is, we've been talking about this within a couple of papers, but in fact, all the other works that I mentioned fall in this non-interactive approach where the sample complexity does have to linearly increase with the number of agents. So how can interaction actually help collaboration? And I think it's helpful here to think about collaborative protocol as a form of game solving. Can I know how many of you are familiar with min-max games or just min-max equilibria? Okay, so more than half of you are familiar with this, which is great. Even if you're not, this is actually, I'm just going to give you a few keywords and where you can look more. You can reimagine collaborative learning as a way of solving a zero-sum game. What is that meaning? Well, it really means that imagine a world where two players are playing against each other. Each one of them is trying to make the other person's life miserable. If we know how to deal with that kind of game, which is called a zero-sum game, then we can use the same ideas to solve this. Why? Because this objective that I wrote, you can think about it as having two agents, a minimizing agent and a maximizing agent. The first agent is trying to minimize the loss. The second agent is trying to maximize the loss. And minimization is happening over a space of models, and maximization is happening over a space of distributions. So when this optimal thing is happening, this is actually called a min-max equilibrium. And if I have a little bit of an epsilon here, this is called an approximate min-max equilibrium. The important thing about this game solving idea is that we've known for decades actually how to solve these games. And one approach to solving them is to imagine the two players to play a no-regret optimization against each other. In fact, you can think about one of them doing a no-regret optimization, which is follow the regularized leader, or like stochastic, like online stochastic gradient descent. And the other player is doing best response, which is essentially saying that they're doing ERM. And then if you kind of put these together, what we know is that you can get this approximate min-max equilibria, and the sample complexity of getting to that is a sample complexity that the min and the max player would have needed to do this thing, which is to run an ERM and to run a no-regret algorithm. So the sample complexity just translates to the sample complexity and regrets of those two players. To say a little bit more, I just want to give you a little bit less of an abstract way of thinking about how these two players are actually playing against each other. So the min player is the best responding agent. This is the agent who's going to be running ERM. What are they running ERM over? Well, they imagine that every time step, they're dealing with a mixture distribution over the current groups. And the mixture weights alpha 1 to alpha k is given to them. So they come in, they look at a mixture of the distributions, and they need to do ERM over that. So naturally, what they have to do is to actually take samples from this mixture, or take samples from each of those distributions weighted by these alpha i's, and then run the ERM. The max player is a no-regret algorithm. So what a no-regret agent must do is that it must actually maintain a distribution over these k different groups, because that the max player, recall, that was trying to maximize something over the k people. So this maintaining this distribution, these are the alpha i's actually that the first player was using. So these are set by the max player, and they're set in a way that it's no regret. I'm not going to go into the details of what that means, but essentially these alpha i's are a proxy for how poorly so far our models that we have learned at every time, these models that the min player is learning, is performing on each of these distributions. So the worse the performance, the higher the alpha. So now what this means is that to actually perform these two things, I need to sample. I need to sample in two places. Recall that I need to sample for the ERM, where the samples are coming from the i's, kind of weighted by these alpha i's. And I also need to sample to know how poorly my previous models have been doing so far. This is a very easy sample. I just take a few samples, maybe even a random one, to see how my test error has been doing. And interaction is exactly happening at these places where we keep going between the two. What is the interaction? The min player is doing ERM, and it has to take samples from all the DIs. But this number of samples taken was based on a proxy of how each distribution was doing compared to everybody else. So that's the interaction. The fact that how much more I contributed took into account how much worse or better I was doing than everybody else. So it's interesting that even with this small and pretty easy to consider level of interaction, we are able to get these results. So this was an example of doing this ERM versus no regret. This actually does get the logarithmic result that I was telling you, but to get truly the optimal bounds, you need to be a little bit smarter, and we do this by solving these games kind of optimally using mirror descent and introducing a theory that really allows you to think about how to solve these problems. So if you're interested in, or if you see this type of problem popping up again, this is, I think, one place that you can go and think about what kind of optimization you can deal with, and the fact that these are actually quite distributed looking computations. So really the technical message I want us to take away from this part of the talk is that you can think globally, but you have to act locally. And the way you would do that is that you think about minimization of regret as a medium for these agents. Okay, so in the last, I have 11 minutes, is that right? Okay, so in the last 7 minutes, I'm going to talk a little bit about going beyond accuracy guarantees. And these are kind of saying that not only I want to provide accuracy guarantees per groups, but I also want the amount of accuracy that each one of them is getting to be a fair return on how much effort they're putting into this collaboration. And effort here could be the number of samples, could be computation. Let's focus on the number of samples. In a sense, what we're asking is that how can we achieve those desirable per agent trade-offs between accuracy and samples? So this suggests that we need a theory for multi-agent sample complexity. And I want us to think about what are some aspects of almost like an axiomatic aspects of thinking about these theory of multi-agent sample complexity. Well, the fact that whatever number of samples I suggest that somebody has to provide has to be a reasonable share of data. Now, what is reasonable? Well, let's talk about what's definitely unreasonable. It's unreasonable for me to ask you to provide an amount of data if I'm asking you to provide more data than you could have used locally to learn by yourself and forget about everybody else. So this is something called usually individual rationality, that you should strictly benefit from, like essentially strictly do less work if you come to a collaboration than if you were to do something independently. Another unreasonable aspect is if I ask you to provide some data, then essentially part of that data is exclusively being used to meet somebody else's objectives rather than to actually help you meet your own objective. It's unreasonable again because you had no responsibility towards the other person. You would have been happy to help them as long as you help yourself too, but you don't want to go against your own benefits. So these are two unreasonable shares of data. We introduce these as axioms in an ICML 21 work, and we call them two things, individually rational and stable equilibria. And they're exactly what I told you. So something is individually rational. There's kind of a collected sample. These are the samples I tell you to provide. It's individually rational if whenever you could actually meet your own accuracy guarantee, you were spending no less than what I asked you to provide. And something is a stable equilibrium if I ask you to provide something, and whenever you provided any less of that while everybody else remained the same, then your own constraint would have again failed to hold. So essentially, I ask you to provide a number of samples that any reduction of it will strictly impact your own happiness. So why do we care about these rationality and equilibria? Well, there are about the welfare of agents the way that we introduce them, but it's also about usability and stability of these federated learning systems. Because if even a small reduction, an agent feels like they can reduce their own contribution by a small amount, and if everybody thinks that, then I'm going to be left with a data set that is so small that I cannot actually use. And in the spirit of saying that these are not only theoretical issues, this is an example of popular data sets. We have tested this on a number of data sets that shows that typical federated learning algorithms like FedAverage and many others actually leave a lot to be desired, which is that something like 60% of agents think that unilaterally they could provide as little as 5% of their own data, their current share of data. And of course, if even 1/3 of them, like even half their own data set, we get to a point that our training error doesn't even converge. So this is a real problem for the stability and long-term usability of the system. So we do really need to address them. So what are some theoretical insights we have here? Okay. The first thing is that do these always exist? I have a little bit of a bad news. The stable equilibrium doesn't always exist, but it exists in most cases that you care about. I'm happy to talk about what that means in the break. But The other piece of medium news, which is not great, but it's not that bad either, is that sometimes, while they do exist, they still require a bit more data on average than that optimal collaboration would have needed. Which means that in the best equilibria, sometimes some agents just shouldn't contribute anything at all. There is a free riding aspect to it. Which means that what we have to really think about is when we go from optimal collaboration to equilibrium, we should think about judiciously introducing some small inefficiencies, asking some people not to contribute as much, or not relying on their contributions if they don't. So let me give you an example of why this is happening. So this is an example where optimal collaboration and equilibria or individual rationality look very different. Imagine a setting where you have one agent whose data distribution is very generic. It actually intersects everybody else's data very kind of evenly. And then you have all these specialized populations. Then in an optimal collaboration, in fact, that generic distribution can do all the work. They can just really very well learn a model. And because the model is so high quality here and there's a lot of intersection, the model is actually of reasonable quality for everybody else. So optimal collaboration, just a central agent does the work. But actually for individually rational or equilibria, the central agent should do no work because their data is so generic that if all of these agents met their learning guarantees, the learning guarantee on the generic data would have also been met. So this is the exact trade-off between being the best at solving a problem, so you can most efficiently solve it for everybody else, but because you're also the best at solving it, you should be doing as little work as possible in an equilibrium to solve it. And this shows that sometimes this gap between an optimal equilibrium and optimal collaboration, like the first part of the talk, could be as big as root K, sorry. And I wanted to just end by saying that this is not necessarily all bad news, because something that you find here is that while free riding should be part of the equilibria, we shouldn't rely on some people to provide samples. The beautiful thing that's happening here is that the existence of free riding doesn't actually change optimal collaboration, because there is still everybody else who should contribute is actually contributing in an optimal way, as if you're back in the first part of this story. So I think this is really interesting because we shouldn't just worry about free riding, because sometimes free riding doesn't impact the global scale at which and how people collaborate. Okay, this is all I wanted to say. And in addition to kind of the mathematical theory that I was introducing, I just wanted to think about this as also a call to do more of a mathematical foundation for sample complexity. Because for these collaborative, federated, multi-distribution learning settings, we do need to have these algorithms that are acting globally. But in fact, it's a very much of a local computation or local incentives and objectives that should matter in our theory. So we should really try to bring these together. Okay, that's all. Happy to take some questions.
Yeah, so there have been some famous results on the learnability of Gaussian mixtures. The stability of the problem depends on how small the smallest alpha is. It's like a rare Gaussian component. Or maybe even one of these terms, how close any pairs of components are in maybe total variation distance. So basically, bigger alphas are nicer for learning Gaussian mixtures in terms of them being a stable problem. Does that somehow characterize into what causes alphas to become bigger, or like the direction of alphas in the Maxman game you're playing? Because there's a.
So I think so that's a good question. So one of the things you're asking is that how much more am I going to focus on one person's distribution and ask them to provide more samples if other people's jobs are too far or too close to it? So this is rather, I mean, the example of Gaussian learning Gaussian distributions is interesting, but I would say that this is actually closer to the whole area of thinking about boosting, because that's also what we do. We repeatedly try to focus learning in a subset. And we have a very good theoretical understanding of what happens, so that in fact, we do have algorithms that make sure that we never put too much weight on an individual. So all of this area, in fact, online gradient descent, boosting, smooth boosting, all of these are connected in a really elegant way to control the amount of weight we are putting on any one agent. And it does kind of come in again later in the second half of the talk, because the more weight we are putting on somebody, sort of the worse they were doing in comparison to everybody else. And ideally, we want to keep these as close as possible when we are trying to think about equilibrium, because it removes too much of an incentive to deviate. But great question. I think there was another one.
Yeah, I have kind of a related question. So for the min-max formulation, I wonder if setting some sort of minimum level on the worst case accuracy, per group accuracy, sometimes comes at the price of lowering the accuracy for the people who use distributions.
Yeah, so you're talking about you're talking about okay, you're talking about this is potentially making the benchmark very uncompetitive, because there is somebody's distribution who's just too difficult to learn or very different from everybody else's. So that's a great question. We think about this as sort of the most robust benchmark, but actually you can change this benchmark. It doesn't have to be min-max. You can think about, and people have thought about slightly different benchmarks. In some way, this is like an L-infinity benchmark on the performance of k different populations. The average performance, the typical thing we think about, is an L1. And you could kind of think about going between these two ends. There is a little bit of work, not quite a lot of work, but I think it's an interesting area. And there's some works that axiomatically address what are the good opts to put here. And in general, I think it's a really worthwhile area to think about. Any other questions?